Let's dive into the fascinating world of quantum computing by creating a simple quantum circuit in Python. We'll simulate quantum measurements, and later, we'll explore an actual real-world application of quantum mechanics called quantum key distribution, or QKD. Stick around till the end, because this is one of the coolest uses of quantum technology. Alright, so let's start by building a basic quantum circuit to demonstrate the core concepts of quantum mechanics, like superposition and measurement. In the first cell of our code, we begin by importing the essential libraries. We're using Qiskit, which is an open-source framework for quantum computing, and we'll also use Air Simulator for running simulations of our quantum circuit. Finally, we use plot histogram from Qiskit's visualization tools to make our results more intuitive. Now, in this simple example, we create a quantum circuit with just one qubit and one classical bit. Think of the qubit as our quantum information carrier, and the classical bit is where we will store the measurement result. In Qiskit, setting this up is straightforward. We define our circuit like this. Think of a quantum circuit as a series of operations or gates that we apply to qubits. It's the fundamental structure for building quantum computations. Here we are creating a new quantum circuit object using quantum circuit constructor. These arguments specify the number of qubits and classical bits in our circuit. The first one represents the number of qubits. Qubits are the quantum equivalent of classical bits. They can be in a superposition of 0 and 1, unlike classical bits, which are either 0 or 1. The second one represents the number of classical bits. Classical bits are used to store the results of measurements we make on the qubits. When we measure a qubit, we get a classical bit, either 0 or 1, as the outcome. Therefore, this line creates a quantum circuit named QC that has one qubit and one classical bit. With this, we now have a blank slate. Next, we apply a Hadamard gate to our qubit using the H method. The Hadamard gate is incredibly important because it puts the qubit into a superposition state. Without getting too mathematical, a qubit in superposition exists in a state where it has a 50% chance of collapsing to 0 and a 50% chance of collapsing to 1 when we measure it. This is the magic of quantum mechanics. Probabilities rule everything. Now, to actually measure the qubit, we call QC.measure, which means measure qubit 0 and store the result in classical bit 0. With this, our circuit is ready. Next comes the simulation part. We use the Air Simulator, which is a powerful backend provided by Qiskit for simulating quantum circuits on classical computers. We run the circuit using run method. We are passing our circuit variable QC as arguments here. Then we collect the results using a result method. We also get the measurement counts using getCounts method. Finally, we print the measurement counts. For those who are curious, what we're doing here is running the circuit a default of 1024 times. This is called the shots in quantum computing. Each shot is like flipping a quantum coin. Sometimes you'll get 0, and other times 1. These results are stored as counts, which we can visualize in a histogram. When you run this, you might see output like this. This means the simulator detected approximately half 0 and half 1 outcomes, which makes sense because the Hadamard gate gives a 50% probability for each state. We also display this visually using plot histogram. If you look at the histogram, you'll see two bars, one for 0 and one for 1, which should be roughly equal in height. Now that we've warmed up with this basic quantum simulation, let's move on to something much more exciting: quantum key distribution, or QKD. In the second cell of the code, we simulate the BB84 protocol, one of the first and most widely used QKD algorithms. It's based on the fact that the act of measuring a quantum state changes it. This is crucial for secure communication because if anyone tries to intercept the information, it will be immediately detected. Let's break this part of the code down. We simulate two people, Bob and Alice. Bob wants to send a secure key to Alice, but an eavesdropper might try to intercept the communication. Using QKD, they can ensure that any interception attempt will leave a trace. First, Bob generates random qubit states. He creates random bits, Bob bits, which are just zeros and ones, and also random bases, Bob bases. These bases can either be the standard basis or the Hadamard basis, represented by 0 and 1. Similarly, Alice also generates random bases, Alice bases, to measure the qubits. We then iterate over 3 lists simultaneously: Bob bits, Bob bases, and Alice bases. Zip function pairs up the elements from these lists. Inside the loop, we are creating a quantum circuit with one qubit and one classical bit for each bit being transmitted. For each bit, Bob encodes these bits into qubits. If his bit is a 0, and he chose the standard basis, the qubit stays in the 0 state. If it's a 1 in standard basis, it goes to 1. Remember, Bob basis will be either 0, standard basis, or 1, Hadamard basis. If it's 1, we apply the Hadamard gate, using H function, to the qubit. If he chose the Hadamard basis, a 0 becomes a superposition, and a 1 becomes another superposition. He sends these qubits to Alice. Alice, our receiver, also randomly chooses a basis to measure each qubit. Just like Bob, she can choose either the standard or Hadamard basis, completely independently. She measures each qubit she receives, and gets a result of 0 or 1. The crucial point here is that if Bob and Alice use the same basis, Alice's measurement will correctly match Bob's original bit. But if their bases don't match, the result is random. This misalignment helps identify whether an eavesdropper has tampered with the communication. Next, we simulate the quantum circuit execution. We use the air simulator to run the circuit and get the measurement counts. Since we are ideally expecting one of the two values 0 or 1, we get the more likely value. Max function gets the most frequent measurement result from the counts dictionary. In an ideal simulation, you'd expect just one key in the counts dictionary. Finally, we append the measured bit, converted to an integer, to the Alice results list. This list will store all of Alice's measurement outcomes. So, in summary, this loop simulates the process of Bob encoding bits into qubits based on randomly chosen bases, Alice measuring those qubits in randomly chosen bases, and storing Alice's measurement results. Each iteration handles one bit transmission. Finally, we create the shared key. This list only contains the bits where Bob and Alice use the same basis. Bob and Alice compare their bases. This part happens in public, and they discard any bits where the bases don't match. The remaining bits form their shared key, which is secure due to the principles of quantum mechanics. In this simplified example, we're just doing it for 5 bits, but in a real-world scenario, they would do this for many, many bits to generate a long, secure key. This is a simplified version, but it captures the essence of how quantum key distribution works, leveraging the principles of quantum mechanics to achieve secure communication. We also print the results. If we run this code, the output shows Bob's bits, his bases, Alice's measurement results, and most importantly, the shared key. This shared key is what they can now use for secure communication. Here, the shared key is derived only from the positions where Bob and Alice use the same basis. For the first bit, Bob's base is 0, Alice's base is 0. They match. Bob's bit was 1, and Alice's result is 1. So 1 is added to the shared key. For second, third, and fourth bit the bases don't match. For the fifth bit, Bob's base is 0, Alice's base is 0. They match. Bob's bit was 0, and Alice's result is 0. So 0 is added to the shared key. Therefore, only the first and fifth bits are used to form the shared key 1, 0. The other bits are discarded because Bob and Alice used different bases to encode and measure them, respectively. This is the core of the quantum key distribution idea. The cool thing is that if an eavesdropper tried to listen in, the bases wouldn't match, and the shared key would be invalid. Even if an eavesdropper intercepted the qubits, they wouldn't know which bits to keep for the key unless they knew both Bob's and Alice's bases. Because the bases are randomly chosen, the eavesdropper has a very low probability of guessing them correctly. So why does this matter? Quantum key distribution is already being implemented in secure communication systems to protect sensitive information. Major institutions are experimenting with QKD to secure bank transfers, government communications, and even medical records. And that's a wrap for this tutorial. We went from understanding the basics of quantum circuits to simulating one of the most groundbreaking applications of quantum computing. If you found this useful, or you want to see more quick coding challenges like this, check out these videos on this channel. Thank you for watching, and I'll see you in the next video.